Thank you for having me. This is a little bit of about my thesis project, and so we're going to talk about the top-down activity. We are trying to watch this activity in the cochlea. Uh, we know that subjects with tinnitus have a peripheral and central origin. Most of the subjects with tinnitus have some level of hearing loss. So I think we shouldn't stop researching on the cochlear activity, even though we recognize that cerebral activity is the origin of tinnitus nowadays. We think that the cortico-cochlear modulation on the auditory efferent system should be better understood, and we can maybe have some new insights on the efferent system and tinnitus. So residual inhibition is actually a very valuable paradigm to study the dynamics of cochlear activity and dynamics of the brain in tinnitus. So basically, we have seen a couple of important papers on using and understanding residual inhibition as a mechanism to have better insights on tinnitus pathophysiology. So we try to investigate cortical and cochlear oscillatory activity during the residual inhibition. And for that, we're going to have a looking for the frequency bands specifically that are modulated on subjects that are responders and non-responders to this residual inhibition paradigm. So some of the classifications that I'm using for doing this separation of subjects is that the subjects that do not respond will have a less than 30% of reduction in tinnitus, and subjects that respond have 30% or more of the reduction on tinnitus after the noise exposure. So basically, this is very experimental. Some of the papers that you can see down here have a 50% threshold, but still very experimental thing to do in perception, because at 30%, you already have some level of change in perception after the noise. So also, I would like to tell a little bit about this very recent paper of people in Tübingen that have been speaking about cochlear activity in tinnitus. So what we did basically, we so far have been recruited 22 subjects, and where they were aged between 18 and 55 years old. They must have 3 or more months of chronic tinnitus. That the subtype that we're studying is mostly chronic, more than 3 months, and bilateral or mainly unilateral tinnitus. We asked them to have a normal hearing thresholds, but on the clinical paradigm of normal hearing thresholds. No history of neuropsychiatric disease, of course, not use of any medication that could change the EEG activity. And also we wanted to classify them, as I said before, in 30% or more as responders. That give us 10 versus 12 subjects. And our data basically is in the right plot. We see that a group of subjects had to be, a couple of subjects had to be retired from the sample because they have residual excitation on my paradigm. But most of the subjects are very well distributed on the responses to the noise. And how did we do this? We basically have a simultaneous record using EEG of the 35 channels, and we use a stimulation of noise via bone vibration. We use a Gaussian noise, set it at 10 dB over the minimum masking level for each subject at the frequency, centered at the frequency of the tinnitus. And simultaneously, we collected DPOIS, distortion product autoacoustic emissions during the before and after the presentation of the noise. We selected 1 second window for this DPOIS to do a Fourier transform and have the frequency bands of the envelope of that DPOA. So we're analyzing the variation on the amplitude. You can maybe see some more information on this method on this paper from Zakisevich. But basically, we analyzed for this presentation. As I'm doing an exploratory presentation, I did an FZ channel analysis and a DPI envelope analysis. Also, for this specific analysis, I calculated the PSD, the power spectral density, and the aperiodic component, the 1/f slope, for this specific channel. Well, if we look very briefly to the microphone on the DPIA, we can see how was the experiment. Very simple. We had a resting state period of 15 seconds pre-stimulus DPIA. The noise presentation is very clear. And after that, we have an analysis of the first 15 seconds where the perception change is more pronounced. So we're only looking at the 15 seconds pre and 15 second post noise stimulation. And what were the results so far? Well, if you look at the time frequency analysis of the FZ channel, we see that after the stimulation, the non-responders group have a relative high gamma band activity compared to responders group, and also some below 10 hertz delta activity that was higher compared to the responders group. Even though this is only for the FZ channel, I didn't see any significant difference after permutation analysis. I was looking for any clusters, but there was no significant cluster. After that, we looked at the different bands separated. But when we compare both groups, between groups, there was no significant difference between them in any of the bands. But within groups, when we analyze only the non-responders group and we compare the pre to the post segment, we see a delta increase in the non-responders that is significant and that is not present in the responders group. But in the responders group, there was some weak difference in the beta band and the pre to post. That difference was a reduction in this band specifically. After that, we wanted to check if there was a slope difference between those between the groups, and actually we found that after calculating the non-periodic 1/f, we saw that the non-responders group previous to the stimulation, I mean before any noise exposure, we saw that they have a stepper 1/f slope, and that was significantly different from the responders group. So what is interesting is that after, if you look at this bright orange one, after the exposure, both groups tend to be similar. So there are some changes in the exposure of the noise to the noise that makes the dynamics kind of similar between the groups. These are the references for this kind of analysis. And I have to remind that this is only for the FZ channel. So after that, when we look at the cochlear activity, we see that on the envelope analysis, we see that there was a significant difference in the theta and beta and gamma band. That is, it's very clear in this plot that we see that from pre to post, activity in the non-responders group, we see an increase in the power of the oscillation, and it was statistically significant for these three bands. But on the responders group, on the other hand, we see only a reduction in the beta band, that it was more clearly in this section of the graph. So the cochlear activity is kind of different. It is responding different for each group, even in the different directions of the power. So basically, so far we have seen distinct modulation patterns of power spectral density in both EEG and DPOI channels, and showing different tendencies according to groups. Also, there were differences in the delta, theta, beta, and gamma bands, but mostly delta and gamma bars were more consistent across analysis, and that's what the literature has been telling us before. So specifically the non-parametric parameters, I think we can use it for understanding the dynamics instead of using just separated frequency bands. And maybe focusing on the 1/f slope can be particularly useful. And actually, one recent paper from Chao's study showed that using machine learning, the 1/f slope was very helpful to differentiate between the groups of responders and non-responders. So also the DPOI activity might be useful for biomarkers and help us understand some of the specific in the peripheral activity of the auditory system. And I have to say that this might be the first experimental design to assess this activity in residual inhibition. And obviously, we need further analysis and research to clarify these results. We need larger sample sizes, and that's necessary for establishing mechanistic theories. And we'll keep on working on that. So that's it for today. Thank you.